Hey everyone, today we're going to tackle one of those ideas that sounds kind of complicated but is actually all around us, from nature to the code running on your phone. We're talking about recursion. And once you get it, I promise, you're going to start seeing it everywhere.
But, before we throw a textbook definition at you, let's do something a little more interesting. Let's go on a hunt for a hidden pattern that connects a few things you probably see all the time.
Okay, so what in the world could a family tree, a folder full of files on your computer, and a weirdly beautiful shape like a fractal possibly have in common? I mean, on the surface, they're completely different, but there is a deep connection here. Think about it for a second.
Did you get it? The secret is self-reference. Each one of these things is defined, at least partly, by itself. A person has parents who are also people. A computer folder can hold files, but it can also hold other folders. And a fractal, well, that's the most obvious one. It's a big shape made up of tiny, perfect copies of itself.
So this powerful idea, this pattern of self-reference that we've just uncovered, well, it has a name, and that name is really the key to the whole thing.
And there it is, recursion. At its heart, it's just the process of defining something in terms of a smaller version of itself. It's a way of taking a big, complex problem and breaking it down into smaller, bite-sized pieces that look exactly like the original problem.
Okay, but here's the catch. For recursion to actually work, especially when we're talking about code, it can't just go on forever. It needs to follow two really simple but absolutely non-negotiable rules.
So every recursive algorithm is split in two. You've got the general case, that's the part that does the recursion, the part that calls itself to solve a slightly smaller piece of the puzzle. But the real hero here, the most important part, is the base case. Think of it as the exit ramp or the stop sign. It's the simplest possible version of the problem, the one we can solve directly without any more recursive calls. It's what stops the whole thing from spiraling out of control.
And trust me, you do not want to forget that stop sign. Because if you do, you get what's called infinite recursion. The function just calls itself, and calls itself and calls itself again and again, forever. Or, well, until your computer runs out of memory and the whole program just crashes. The base case is literally what saves us from this digital black hole. All right, that's enough theory. Let's get our hands dirty and actually watch these rules work in a classic programming example.
We're going to use the famous Fibonacci sequence. You've probably run into this before. You start with 0 and 1, and then every number after that is just the sum of the two before it. It's like it was made for a recursive solution.
So let's say our goal is to find the fourth number in the sequence, which we'll call fib4. The rule is simple, right? To get fib4, we just need to add fib3 and fib2. Easy enough. But wait, how do we find those values?
You guessed it. We do the exact same thing again. The fib of 4 function calls fib3 and fib2. Then, fib3 has to call fib2 and fib1. And fib2 has to call fib1 and fib0. You see this cascade? It's like a chain of command where each step breaks the problem down into even smaller identical problems.
And finally, we hit rock bottom, but in a good way. This is where our stop signs, our base cases, kick in. By definition, we know that fib of 1 is 1 and fib of 0 is 0. There's no more math to do. The chain reaction stops here, and we can finally start getting some real answers. And now the magic happens, what's called unwinding. Those simple answers from the base cases, the 1 and the 0, start getting passed back up the chain. They get added together to solve fib of 2, which then helps solve fib of 3, and so on. All those little answers bubble all the way back up to the top, until, finally, our original fib4 call gets its answer, 3. So, to get that one little number, 3, how many times did our function actually have to run? 9. 9 separate calls. Kind of crazy, right? All that work just to get to 3. And that brings up a really important point about recursion. All of that repeated work means this particular solution has a time complexity of O of 2 to the n. Now, don't worry about the notation. What it means is that the amount of work grows exponentially as the number we're looking for gets bigger. So while this solution is super elegant and easy to write, it can be, well, a bit of a slowpoke. It's powerful, but not always the most efficient tool for the job. But hey, recursion isn't just about crunching numbers. Its real magic, its art, is in solving incredibly complex problems and creating jaw-dropping beauty from just a handful of simple rules. And that brings us right back to where we started, fractals. This quote just nails it. They are the perfect visual representation of recursion. All of that insane, beautiful complexity you see is just one simple rule, repeating itself over and over and over again, on smaller and smaller scales. It's mind-blowing. And then there's the legendary Tower of Hanoi puzzle. It looks impossible to solve, right?
But the recursive solution it's just beautiful. It's 3 simple steps. To move a whole stack of disks, you just tell the computer, hey, first move the stacked -1 disk out of the way, then move the biggest disk where it needs to go, and finally move that smaller stack back on top. That's it. It solves this complex puzzle with pure recursive genius.
So from now on, when you're browsing through folders on your computer, looking at the shape of a fern, or even just thinking about your own family tree, you'll know the secret engine running in the background. You now have the key to one of the most fundamental patterns in our world. The only question left is, where are you going to see it next?